Alright, so today's lecture is about humidity, and we'll just start talking briefly about gas laws. And then we'll dive into this a little bit more here over the next few days. So humidity, basically we're talking about water vapor pressure. Actually then represents the kinetic activity of water molecules in the air. So for the actual amount or weight of water vapor in a gas to be determined, we need to look at the water content, or the absolute humidity must be measured. Okay, and so we're going to define what that means. We'll be talking about absolute humidity and relative humidity. So absolute humidity then is the actual amount or the weight of water that's in the gas or in the air. And the way we measure that is generally in units of milligrams per liter. So milligrams of water vapor per liter of gas. That's the most common unit of measurement for the absolute humidity. So air then that is fully saturated at 37 degrees Celsius, which is equal to 98.6 degrees Fahrenheit, so that's normal body temperature, and at normal 760 milligrams of mercury of barometric pressure, so that would be at sea level, generally then has a water vapor pressure of 47 millimeters of mercury, or an absolute humidity of 43.8 milligrams per liter. So then that is where we get the 47. So when we're looking at normal body temperature and then considering sea level, even though we still use that constant of 47 to subtract because of body temperature when we're figuring out the PaO2, the alveolar AO2 for the alveolar air equation. So that's where the 47 comes from, the water vapor pressure. So then relative humidity is, so when a gas isn't fully saturated, the water vapor content can be expressed as relative humidity. So relative humidity is basically the ratio of the actual water content, or the weight, compared to its capacity. So because of the this PowerPoint I think I did on Google Docs or Google Slides, it was really hard to get the capacity, the word capacity, right underneath content. So it's a ratio. It should be content basically divided by or over capacity times 100. That is your relative humidity percent. Okay, so what the content over the actual capacity, okay, times the 100%. Okay, and then kind of just a little reminder of what that STPD stands for. That's standard temperature and pressure dry. And now this actually comes right out of Egan. It's trying to describe your relative humidity. So kind of looking at an analogy here of comparing the actual amount that's in a cup of water to what the capacity could be. Okay, so this is out of Egan's, out of chapter 6. So when we look at relative humidity, so part A, this is actually in two different slides, A and B. So A here, we're looking at, this again provides an analogy of the relationship among water vapor content, capacity, and relative humidity. So A basically represents heating the gas, which then is going to increase your capacity or the ability to hold water vapor. But the content itself is actually the same. So you can see that every amount in every cup, the full, the 2/3, the 1/2, and 1/3, that's all the same amount of water. However, the capacity, your ability to hold on to that water vapor or to carry water vapor, has increased when you heat something. Okay, so so the various glass sizes represent the capacity of a gas and to hold water vapor. So obviously the larger the gas, or the larger the glass, sorry, the greater its capacity. Oh my goodness, a tongue twister. And then this one here is really looking at the effect of decreasing capacity then as you're cooling the gas. Okay, so in this one, the water in the glasses basically represents the actual water vapor content. A glass then that is half full, as shown in the first picture there, is at 50% capacity or 50% relative humidity. So you have their actual compared to your capacity. And then a full glass would represent being fully saturated or 100%. Okay, so a decrease then in capacity would have the opposite effect with cooling the gas. So that's kind of what we're seeing here in this picture. So this is representing cooling the gas. So it decreases the ability or its capacity. Okay, and then the capacity would continue to decrease, but the amount of water remains the same. And then the spillover is representative of the condensation. So it's just kind of showing the analogy of relative and actual humidity. So when we talk about BTS, or that's body temperature, okay, so body humidity then is the percentage of the ratio of actual water content, which is the weight compared to its capacity at BTPS. So that's body temperature pressure standard. Okay, so at body temperature, or at BTPS, the air can actually hold 43.8 milligrams per liter. Okay, so that's the capacity. So then you would take, to calculate body humidity percentage, you would take the actual amount divided then by that 43.8 and then multiply it by 100. So so then we look at humidity deficit. And humidity deficit, and I'll kind of talk a little bit more about this in just a second as to why we're so concerned about all this. So humidity deficit then basically represents the amount of water vapor your body must add to an inspired gas then to achieve that 100% saturation at normal body temperature at the 37 degrees. So humidity deficit then would be your capacity minus your actual. And then so capacity is 43.8, so minus whatever actual. So the reason that's important is that we want to make sure when we are administering a gas, especially through an artificial airway, or even high flow gas, it really can dry out our body, and that will have the ability to clear mucus and secretions that will impair that ability. Okay, so the sputum and the stuff will get dried up, and then you're not able to cough and mobilize those secretions. So on lower flows, it's not such a big deal, but even as simple as a nasal cannula, which is just your one that you wear on your nose that you see, people have on, at the grocery store or wherever. Once we hit about 4 liters on those, we like to consider adding humidity. And then some of the newer devices that we are able to use now are heated high flow nasal cannulas. So they are actually a larger bore tubing that can actually deliver up to like 60 liters per minute. And then we can also adjust the FiO2. So the normal FiO2 is 21%, that's just our room air, but we can adjust that all the way up to 100% if we need to. So it's another therapy method of delivering oxygen, and those type of devices always run on a heated humidifier, so because of the air again being so dry. Also, when patients are on a ventilator, it looks like they're only going to be on for maybe a day or two, and their minute volume, which means how fast they're breathing, how much volume is going through, as long as they're not having a high respiratory rate or a high volume, they won't get as dried out, but we definitely have to monitor that. And again, depending on why they have the breathing tube, if it's pneumonia related or bronchiectasis or some type of other disease where secretions can be an issue, then we definitely want to put a heated humidifier on these people, because we want to be able to close that humidity deficit and be able to have those secretions be able to move freely as needed. They already are impaired with the ability to cough and mobilize stuff with having an artificial airway, so we actually have to go in there and suction and get that stuff out, but it makes it a lot easier when they're on a heated humidifier. So if they're not just like a post-op where they're going to be on a ventilator for hours to maybe 2 days at the most, we usually put them on what's called an artificial nose, or an HME. It's like a humidified exchange little device that kind of represents, or can, the exhaled gas basically, the water vapor that you feel when you exhale kind of moistens this little filter, and it can serve as a ability to humidify the air. But so that's mainly why our concern is, because as our body warms the air, then the capacity to carry water then goes up. So that's why it's heated. It's not just cool. We can do some blow-by humidifier, which is like a passover, where the gas just goes over sterile water that we have in like a humidifier that's not necessarily heated. But generally, like our trach patients, if they are on an aerosol, because we can actually do cool aerosol or warm aerosol, and we always do a warm aerosol on a trach patient, because your nose is your natural humidifier and your filter, and it also heats up the air so as it comes into the body. So when you're trached at your throat, that bypasses all that natural ability. So again, secretions are an issue to make sure that they're not getting dried up. And I'll have a really good story to tell you guys, hopefully when we get back to class, about a gentleman that had a trach at home. Mainly he actually just had a stoma. The tube itself was gone, but he wasn't using any humidity here in Denver, and you know how dry our air is. It was the most disgusting thing I've ever seen in my life. But so that'll be a good story to share with you some other time. But so anyway, so by the time the air then arrives at the distal airways or the far airways, it needs to be warmed to about 37 degrees. So we're able to set that temperature on those heaters along with how much rain out or how much moisture it actually is able to put out on our heated circuits. And then we would like it to be fully saturated with water. Of course, you have to be careful not to go to the other extreme where you have a lot of extra water in your circuit, and people are getting inadvertently lavaged by all the water that's in the tubing and that. So you have to kind of find a balance. So again, as the temperature then decreases, the capacity of air to hold water decreases. So keeping in mind that cold water can't hold, or cold air rather, can't hold as much water as warm air. So as the air cools, the water starts to condense out into the air. All right, I think enough on humidity there for now. And I know Nicole talks about it also in therapeutics. Okay, and then she'll talk a little bit more like when we use a cool aerosol versus a heated aerosol and all that good stuff, because that's part of oxygen therapy. So gas laws. So we'll be looking at gas laws, and so gas laws kind of help define the relationship among pressure, volume, temperature, and mass. So regardless of the chemical compositions, all gases pretty much behave similarly in their responses to these changes in temperature and pressure. So we use these gas laws to predict how gases are going to change under conditions that we can manipulate different variables. Mass is always constant, so no matter what gas law you're talking about, mass is always going to be constant. So the mass of the gas will never change, even when you're changing the temperature, the pressure, or the volume. And then temperature, if you're using calculations with temperature, it needs to be converted to Kelvin. So that's why we introduced Kelvin as a measurement, a way of measuring temperature. So we're going to talk about Boyle's, Charles, Gay-Lussac's, and the combined gas laws. So that's our kind of coming attractions. The first one, and the only one that we're actually going to be talking about today, is going to be Boyle's law. So Boyle's law has to do with pressure and volume. Okay, so those are the two variables that obviously vary. Okay, so we're just talking about pressure and volume. And how we're reading that is P1 and V1 are like your before situation equals your P2 to V2. Okay, so you kind of can look at that as a before or a beginning and end type of scenario. Okay, so again, pressure and volume is what's going to vary, and then your temperature and your mass are going to remain constant. Okay, so what's going to happen here is as your pressure increases, okay, what is going to happen to your volume? Okay, as your pressure then increases, what do you think is going to happen to your volume? So hopefully you're thinking a decreased volume, okay? And decreased volume then is related to, so think about as you're squishing something, you're decreasing the volume, you're having more collisions, things are contained more, and so you're going to have with increased pressure. Okay, and then the same thing with decreased pressure, increased volume. Okay, so they're inversely proportional. And this is kind of where I was going to try to do a little bit of writing. So I wanted to kind of show an example of the P1 V1 equals P2 V2. So we're kind of comparing this before and after scenario. So we're going to look at a balloon that has 75 mils of air with a pressure, so it has the volume of 75 mils with a pressure of 20 psi, which is pounds per square inch. And that's actually how our gas is measured. When it comes out of the wall, that's what we kind of refer to it as in the hospital, because we have piped in gas from outside. Those big silos you may have ever noticed, I'm not sure, but outside there are big silos of compressed air and compressed gas. So it's medical air, and and oxygen. So we have two outlets. We have one that's oxygen and one that's air. And the green is always the oxygen, the yellow is the air. And those actually, we plug in a device called a flow meter that can then deliver the oxygen. But when you actually push it in, the little things into the wall, there's pressure behind it, and it's 50 pounds per square inch, so 50 psi. And that's generally what all your ventilators and devices need to function. If you don't have enough of that gas pressure behind it, your device is not going to run accurately, and generally it will alarm to let you know that it doesn't have enough pressure behind it. So in our lab in school at Pima, we don't have silos outside that have air or oxygen in them. We actually have just the big, huge, tall H tanks. They're about probably my height, maybe a little bit shorter, and they're big tanks that we have back there. And we probably have about a half a dozen of each, and that's how we get a gas source then to use in our lab to run our ventilators and the other things that we show you. So that's for the PSI. So that's a lot of pressure. So if you, always one of my greatest fears is those flow meters plug in, and you have to push them quite hard, and there's like a little click when you push them, and they kind of lock in place. And every once in a while you'll get like a faulty one where it'll kick back out at you. It's like never keep your head in front of a flow meter because those things can pop right back out. And 50 pounds per square inch is a lot of pressure if you get clunked in the head. I never have, but that's always been a fear of mine. Okay, so we're looking at kind of the math part of basically of this. So if we're going to take the 75, so we're looking at this equation of taking basically 75 is your mils, so that's your volume, times, I'm trying to make a dot, but you know I stink at that. So 50 times, or sorry, 75 times your 20 is going to give you 150. Okay, and so we're looking at a 75 mils per psi. Okay, and then we're going to go ahead and, oh, what am I doing? I'm getting distracted here. Here we go. My family's doing something out there. Okay, well, yeah, that's actually right. I'm sorry. My apologies. So yeah, so we have, so what I'm actually trying to do is that we have 30, then we have 30 for our mils, okay, again, times whatever our question is, okay. Our question on this side of the equation is how much pressure, how much psi, okay. So again, this is mils, this is psi, we have mils over here, so we're looking for psi. All right, so we're going to go ahead and figure out basically what we have to do to isolate. So we know that this is 150. I have to kind of do this in my head, so sometimes I have to remember to kind of figure it out a little bit slower. So 30x, basically, x is what we're looking for. So what we need to do then to isolate x, we should remember now with our lovely algebra, is we need to divide both sides by 30, right? To get rid of it, and divide this side by 30, both sides by 30. So that's going to give the psi, the second psi on the right side of the equation is going to be 50. So 50 psi would be the correct answer. PSI. All right. So at 75 mils, we have a pressure of 20. So we should think then, if we're going to decrease it to 30, it's going to, the pressure then is going to increase. Okay, because now we've kind of squished it. Okay, so now our pressure is going to increase. So it's inversely proportional. So it went up to 50. Okay, so that is Boyle's law. We're going to play a little bit more with it. We're just kind of introing it to it today. And we're going to talk about right now how we would apply Boyle's law. Actually, here's just another quick diagram. Again, showing how with increased pressure, we have decreased volume. That's basically what that's showing. Increased pressure, decreased volume. All right, so one of the places that we would apply Boyle's law is the hyperbaric chamber. So if we have conditions such as an air embolism, where you actually get like clots of air in the blood, or decompression sickness. So Boyle's law then dictates that this high pressure that we experience in a hyperbaric chamber actually exerts a pressure on these bubbles, okay? And on air, which is an air embolism, or the nitrogen, which is related to the decompression sickness from, I guess, deep sea diving or whatever, that are trapped in the blood or in the tissues. So if we can squish those, basically, we reduce the size of these bubbles that are trapped and minimize the harm that they could do. So hyperbaric oxygen chambers can actually be conducted, I've read anywhere from like 4 to 6, even higher of atmospheric pressure. So that's a lot of pressure. But that's one of the ways they could treat it. And then this is actually a YouTube video that I would like you to watch, and kind of explains Boyle's Law. I also have other ones that are on Charles and Gay-Lussac's, and then I'm going to have an experiment for you guys to work on your own for next week at home, but I'm not going to give that assignment to you today. Okay, so today's assignment, I do have, let me see what this next slide shows. Oh, these are just my references. I can't remember off the top of my head. So your actual homework then for this, for today, is you do have a chart that I just want you to fill out as a study guide. That's going to help you just kind of understand the, kind of compare the gas laws to each other. So that is really not an assignment per se, as it is just a study guide or a tool for you to use. And then the other thing that you have, so you have this gas laws table. Again, I have on there that is just to help you organize and study the gas laws. And then you have a take-home MRE, and I don't know if they've talked to you about MREs. They're basically a quiz, or like a memory recall. So they're counting the same basically as percentage-wise, or how much they're weighted as a homework assignment. So I'm just, when I've used this in the past, I've given it to students to go ahead and take home so they can use their notes on it. And it's like 20 questions. And it's just a variety of different exercises that we've kind of covered up to so far, because your exam that you have for today, that's for Friday, does not cover the gas laws. So that is it until next time. So that MRE will be due then on Monday, June 1st. So hopefully we'll get to meet in person maybe next month. I'm keeping my fingers crossed, guys. So we'll talk tomorrow at our Zoom.